click, off, click your nitrile gloves. Discharge. Hello and welcome to Starborn Science. Today I will be showing you how to make I forgot an S. C. So I'll be showing you how to make the Mazilli ZVS oscillator, which is a circuit I'm using to drive many of my Tesla coils. And I forgot to draw a node here as well and here as well, in order to not confuse you with overlapping wiring. So, a quick rundown. Current comes from here. Well, it actually comes from here, but I'm gonna discuss this thing from the 1800s, from where electricity flows from. So we're gonna suppose it runs from here. So these two inductors you see is these two things we're gonna wrap in magnet wire, which are not ready yet. These two are our MOSFETs, which are our switching elements. These two are our gate resistors, the things that connect to the gate of the MOSFETs. These little things over there are the Resonant diodes that protect the gates from overvoltage. These here, and are rated for 15 volts. As MOSFET gates cannot go over 20 volts, they say goodbye, F off, much smoke comes out of the components and you're done. And these are the 10,000 ohm pull-down resistors that connect from the gate to the source of the MOSFET, parallel to the Zener diodes. And this is the resonant capacitor, which is this polypropylene capacitor. And I would not like to deviate, would not like you to deviate from the values of the components I'm showing you over here, because I am showing you an oscillator that is able to run a Tesla coil. So if you follow these specifications, you will be able to run a Tesla coil that usually runs, a medium-sized Tesla coil that usually runs about to 380 to 420 kilohertz. So at least that's where my coils run at. So I consider that about, my benchmark. So this is the circuit, badly drawn, because, well, I don't draw circuits very well. I'm not an electrical engineer, but I can make circuits. So today I'm gonna drive you through step by step how to put this thing together. So if you follow my instructions, you will definitely end up with a prototype that works. So yeah. So the last very important bit is these black two diodes. I've drawn them in black because they're very important. Their polarity is very important. I'm not gonna confuse you with cathode and anode. I'm gonna tell you about the black and white part, the stripe. The white stripe goes from actually the black part of the diode goes from the gate of one MOSFET to the drain of the other MOSFET, and the black part of the other diode goes from the gate of the other MOSFET to the drain of the other MOSFET. This is the polarity. Do not change the polarity. If you do change the polarity, the circuit will not oscillate. It will stay there, and your MOSFETs will become resistors and heaters. So do not use any type of diode. Use ultra fast diodes. Use ultra fast high voltage Schottky diodes. I do not care about what kind of diodes you use. Use high voltage fast diodes. In my case, I'm gonna use UF 5508 diodes. There are 1000 volt 3 amp ultra fast diodes. So yeah, this is the last very important component. Now, of course, as I said, I do not want you to deviate from the components. I know ferrite colors are not universal, however, this kind of ferrite is usually a low inductance ferrite used for high frequency applications, and it's colored this way from one side and this way from the other side. And I've bought it from several manufacturers from several countries, and it's always the same kind of material. So the material of the ferrite plays a very significant role at the resonant frequency of the oscillator, and so does the resonant capacitor. This capacitor is 150 nanofarads, not 200, not 100, 150 nanofarad. It's not an electrolytic, it's a polypropylene. It's not a film capacitor, it's a polypropylene capacitor. It's a 150 nanofarad, 1000 volt rated polypropylene capacitor. Now, I'm not claiming that other 150 nanofarad capacitors won't work, just saying this is what worked for me. So you might get a lower or a higher ESR capacitor. If you do get a lower ESR capacitor, then you know, that's good for you. If you get a higher ESR capacitor, you'll get it to heat up faster. That's what you get. I can't help with that. All I can help with is, if my camera focuses, show you it's a peel core. Something. Sorry, it's a polyester. Not a polypropylene, it's a polyester capacitor. It's a MKP, I think that stands for polyester. Otherwise it would say PP, not MKP. In any case, it's a 1000 volt, 150 nanofarad capacitor. Now, of course, I'm not gonna sit here and show you me winding the coils. However, I am going to wind them with 1mm double enameled copper wire. You can use a single enamel, doesn't matter. It's just time that, because you know I have MOSFET. It's the same reason I'm using plastic washers on TO247 MOSFETs. You know, they're not needed, but I use them. So I'll be back when I wind the toroids. So, with my severely wounded from EMI interference LC meter, I will measure this and it comes out at 0.01 millihenry. Well, I've measured this with a more precise instrument, which is also now dead, and it comes out to 14 microhenries per toroid. So this is the value you want. So the toroids are both wound, both measured, and came out the same value, same number of turns. The enamel is scraped off where the connections are gonna go, and now we can start building the things slowly, step by step. And I swear that if you follow the video, you're gonna end up with a working ZVS module. Also, its self-resonant frequency will be around 68 to 70 kilohertz with no load attached. I can say that with certainty because I've built several of them with the exact same components. So yeah, let's mount the MOSFETs on the heatsink. Let's drill some holes on the PCB to mount them on and proceed. So first, as you can see, we have mounted the MOSFETs on their heatsinks symmetrically, and we have the leads exposed. And what you wanna do right now is take the sources of the MOSFETs and bend them backwards. Like this. Do the same with the gates. And then take your drains and bend them forward like this. Now, I'm not doing this for fun. There's a reasoning behind it. So you're gonna do this, and now we're gonna install the protection network first, and then we're gonna move to the diodes. So first I'm gonna install the Zener diodes, and then I'm gonna show you how they are installed. Now the Zener diodes, as you can see, come in various colorations. They're usually red, these are yellow, yet they also have a stripe. Again, I'm not gonna go with anode and cathode. What you wanna do is place like that the part that has the stripe will go to the gate of the MOSFET, and the other side will go to the source of the MOSFET, the left pin. The right pin. The left pin is where the stripe goes. Do you see the black stripe? This is where the gate of each MOSFET is. So you're gonna place them like this to each MOSFET and solder them across source and gate, and source and gate. And as you can see, the diodes are soldered across source and gate and source and gate. And now we will add the 10 kilo ohm resistors in parallel with each Zener diode. So this is how our circuit looks so far. We have added the 10 kilo ohm resistors, we have added the Zener diodes, and they are parallel with each other, connected across the source and gate of each of our MOSFETs. And these are the drains of each MOSFET. Now we're going to add the fast diodes I was talking about, and now polarity is really important. So as I said, the first diode goes, do not mess up the polarity, from this MOSFET's gate, from here to this MOSFET's drain to here. So it's simple. From here, this node, to here, this drain. So one diode is in from gate to drain. And please try and be symmetrical. We're not at art school, we're not doing abstract art here, we're doing electronics. Parasitics do matter, especially in high frequency circuits. So do yourself a favor and try and make everything as symmetric as possible. And I'm gonna add the second diode. And this is the second diode that goes from the gate of this MOSFET. Remember, the gate is here on the left side. We're gonna add some solder from the gate of this MOSFET to the drain, the middle pin of this MOSFET, and its opposite of the other diode. And the other diode is connected from the gate of this MOSFET to the drain of this MOSFET. And this is the most difficult part. Now we're going to add the power inductors. These are not chokes. I know they look like chokes and you're used to call them chokes. In this case, these are power inductors. So we're gonna add these now. And we have added the power inductors, which look beautiful, by the way. They're beautiful components. And the goal is to connect these two together, which is pretty simple. and connect these to the drains. However, on this side we do not want this lead to connect on this diode, so we're gonna put a plastic sleeve from a cable on top and only leave this side to touch the drain side of the MOSFET. So, as you can see, the two power inductors are joined over here and the other ends are connected to the drains of the two MOSFETs. And over here we have a protective sleeve so it doesn't make contact with the lead of the diode. Now we're going to add the gate resistors of the two MOSFETs. So the gate resistors, here they are. They are 220 ohms each. And remember the resistor divider I showed you in the beginning. This resistor comes out of here and goes to VCC, which is where our two power inductors connect. And the other resistor comes out of here, this side, and connects again to VCC, and then connects to the gate over here, and this resistor connects from VCC to the gate over here. So let me connect them. So now we got also our gate resistors in place. They are connected like so. This goes to this gate, this goes to this gate. They both meet and connect to the resistor divider. And now it's time to add our resonant capacitor, which will go across the drains of the two MOSFETs. And there you go, now we've added also our resonant capacitor. Now all that's left to do is tie the sources of the two MOSFETs together. I'm gonna use a jumper wire to do that. And then our ZVS Mazilli driver should theoretically oscillate. If it doesn't oscillate, I have fucked up. So yes, let's find out. So because I'm OCD, I went ahead and added terminal blocks for input and output. So input is from the sources of the two MOSFETs and VCC, so from this clamp, and output is from the drains, from the capacitor and the drains of each MOSFET, so from this clamp. So let me give it some standoffs too, and let's give it a test. So now I'm gonna apply power and I'm gonna probe the drains of the MOSFET, of the MOSFETs, plural, and we'll see if we get a nice sinusoidal waveform that correlates to resonance, or we get shit. And when you look at that, oops, my lid fell off. My power supply. Again, let me turn the voltage down. Will you look at that? What did I tell you? Around 73 kilohertz. It's self-resonating. We got a beautiful sinusoidal waveform with an input voltage of 9 volts. We got 57 volts. That's what resonance does, builds up voltage, energy in general. In this capacitor inductor system, the energy sloshes back and forth between the capacitor and the toroids. And I don't see any weird ringing. I think we are good to go. So, guys and girls and whatever word else you are, I don't mind. This is how you make a Mazilli ZVS driver. This is what runs my Tesla coils. When I say this, I mean exactly this. I use the exact same components I use to run my Tesla coils. So if you use the same dimension coils, you'll have the exact same results. So yeah. Also keep in mind that when I'm running my coils, I'm not running the ZVS in continuous wave, I'm pulsing it with a pulse generator. Pulse generator such as this one, an interrupter which gives packets of current to the ZVS for a certain interval, usually 50 or 60 Hertz. So it's not a continuous operation of the ZVS. In the input, the output of the pulse generator would go in and the current would go in from this side. So this is how I would run my coils, not with continuous wave, and that's a very important distinction and has a tremendous difference in arc length for many different reasons. The resonator builds up energy before each pulse. The air gets ionized between each pulse and stays ionized, and then the arcs have a longer distance to expand between each pulse. So pulsing a coil is more efficient than running it in continuous wave. In any case, I have a video on that on my channel, so I will also link to that. Of course, you can pulse it in with a simple 555 pulse generator. You do not need a fancy pulse generator with a screen, but with that one you can control duty cycle, frequency very finely, etc. But the point remains the same. Pulsing it is better than continuous wave. So, if you do not believe me when I say it can run Tesla coils, this is the old driver and this is the new driver we've made, that I've installed. Now I will go over there and go over there and turn the variac on. If you don't believe me when I say can run a flyback, there it is, running a flyback from my full bridge rectifier. Now also, if you do not believe me when I say it can run as an induction heater, here again it is. Let me connect it to the power supply. Maybe. So as you can see, it also works as an induction heater. So 3 birds with 1 stone. Not bad, right? So, I know people that this episode of Starborn Science didn't have much of a wow factor because there was not much to say. It was a how-to video, but that was the point. The point was to show you how to build this and how to build this exactly. And I hope I passed the point across on how to do that. So yeah, this can also be used as an induction heater. This can be used as a flyback transformer driver. This can be used as an wireless power transmission driver. So it has many uses, not only Tesla coils. So that's why I use it very often, and that's why I considered it would be important to share it with you guys as a couple of people asked me for how to build their own Tesla coils and their solid state Tesla coils and go beyond the level of building a simple layer exciter. So my proposal before going anywhere to mains power Tesla coils was this. So yeah. In any case, I hope you enjoyed this how-to episode of Starboard Science. Keep dreaming, keep exploring, keep building, and I will see you on the next one.